In this video, we're going to look at graphing functions of the form y is equal to a to the x, where a is a positive constant. These are exponential functions and they're often used to model growth or decay. So we can see now that the variable is the power. This is just a constant, so we might have y is equal to 2 to the x, 4 to the x, 1/2 to the x. We can see now a is greater than 0 as these now are not defined for negative values, and also we say a is not going to be equal to 1. If we have 1 to the x, we end up with a straight line. What we're going to do is consider two different scenarios. We'll consider when a is going to be greater than 1 and then when a is going to be between 0 and 1. So let's now look at a greater than 1. So an example might be 2 to the x, 3 to the x, 5 to the x. We might even have e to the x, which is the exponential function. We study e to the x later on. So let's just draw a quick sketch, and what we've got now is our coordinate axis. All of these will have a similar shape, so we'll have them looking something like so. So we will get very steep, very big, very quickly. Unless we transform the curve in any way, we will have the point now 0, 1. That is where the curve will pass the y-axis. So if we consider now 2 to the power 0 is 1, 3 to the power 0 is 1, they will all go through the same point unless transformed. We also have the x-axis as an asymptote. We know that y is equal to a to the x can never be 0, 2 to the x can never be 0, 3 to the x can't. So we have this asymptote. As our value of x gets large, so we can say as x tends to positive infinity, y also gets very large, and y tends to positive infinity. So let's say we've got y is equal to 3 to the power of x. This is a positive constant and it's greater than 1. If we think 3 to the power of 0 is going to give us 1, 3 to the power of 1 is going to give us 3, 3 to the power of 2 is going to give us 9, 3 to the power of 3, 27, then we're going to get 81, 243, and then we're going to keep going up 729, and it's going to get very steep very quickly. We can say as x tends to negative infinity, which is going to be going in this direction, y is going to tend to 0. It will never be 0, and that's why we have the asymptote. So, unless these graphs are transformed, y is equal to a to the x, where a is greater than 1, will look something like so. It will pass through the point 0, 1, and we will have now the x-axis as an asymptote. Let's now consider when a is going to be between 0 and 1, and these, of course, are not included. We're going to now have a scenario where we're modelling decay. So if we look at this now, we'll go the other way. So what we've got then is the scenario now where we have, and we'll do an example of this. This time we will come through, and now the curve will come down, and the x-axis will still be an asymptote. This point will still be 0, 1. So let's say we've got y is equal to 1/2 to the power of x. So our value of a is a positive constant, and now we're between 0 and 1. Again, we have this x-axis as the asymptote, so we can go ahead and put that on. If we consider now what happens as x gets very large, we can say as x tends to positive infinity, y will tend to 0. We can say as x tends to negative infinity, y will tend to positive infinity. So y is going to get very large. Now, if we look at this here, y is equal to 1/2 to the x. I could actually write this now as y is equal to 2 to the power of -1 raised to the power of x. Using the rules of indices, a to the power of m raised to the power of n is a to the power of m multiplied by n. So we could actually write this now as y is equal to 2 to the power of -x. Now if we consider writing it like this, what we have is a reflection in the y-axis. This is of the form now, if we go back to our graph transformations, f of -x. So we can see the relationship between now y is equal to 1/2 to the x and y is equal to 2 to the x. So we have now a reflection in the y-axis. So for example, now if I drew y is equal to 1/3 to the x, then what we'd have just here now is the mirror image, and it would be reflected, and that would model now decay. And if you think about it quite clearly, as a value of x gets very large, negative, this is going to end up getting very big. So if we think about it now, let's say we had 1/2 to the power of -3. We could write this now, turning the fraction upside down and making it positive. We could have 2 to the power 3, which is going to give us 8. So on this particular curve, let's go ahead and put this just here. Let's say we've got -3, 8, and we can see that this is going to get very big very quickly. Yet if I take this point right here now, when x is going to be equal to 2, if we consider now subbing that in, we're going to have 2, 1/4. So that we can see as the value of x gets very big, this is going to tend to 0. It will never be 0, it will never be negative, it just tends now to 0. Let's look at graphing some of these now on a graphical calculator. So we have y is equal to a to the x plus b. So this b is just a constant. As we can see, if we have 1 to the power of x, it's a straight line. 1 to the power 1, 1 to the power 2, and so on and so forth. If I now increase the value of a to be 2, we can see that we start to form now this exponential curve. So it's going to get very big very quickly. On this particular graphing package, we don't have the asymptote shown, but we end up now seeing that that is the x-axis. If I make this 3 to the x, we're going to have a steeper curve, and that makes sense. 2 to the power of 1 is going to give us 2, 3 to the power of 1 is going to give us 3. So this is going to get steeper. So as I increase that value, we can see we're getting very, very steep, and that is going to start giving us very large values very quickly. So for example, now if we take this to 6, y is equal to 6 to the x, 6 to the power of 0 is 1, 6 to the power of 1 is 6, 6 squared is 36, 6 cubed is 216, and so on and so forth. So let's get back down now to y is equal to 2 to the x. So here is our exponential function. Our constant a is going to be 2. What I'm now going to do is add a constant. So if I add 1 to it now, what we're going to have is y is equal to 2 to the x plus 1. The asymptote, although not shown, has moved up from the x-axis to the line y is equal to 1. So this can never be 1 or less. If we just consider now as small or as big negative as this value gets here, this will get very small, but it will never be 1 or less. And we can see moving this now will just increase the asymptote. So we've got now the asymptote here at y is equal to 3. We could go the other way. If I put this down to, let's say, -3, then we've got now the line y is equal to -3. So this now gives us a brief example or understanding of what's going on for values of a greater than 1. So if we go back, what we're now going to do is look at values of a that are going to be between 0 and 1. If I move this back now, we can see that I'm taking this down. So this is 3/4 to the x. So we can see again it goes through 0, 1, and we're going to get now very small as x gets very large. And as we now take this value back, we can see this is going to get steeper and steeper. So if we just put it there, that is now pretty much 1/3 to the x. So we can see now that this is going to be a reflection in the y-axis of 3 to the x, as that's 1/3, which is 3 to the -1. Again, we can move this up and down, and we will have a change in the asymptote. So that gives us a rough idea of what we've got. All of the graph transformations that you've met before can be applied to these curves. So what we're going to do is just work through some basic questions and look at some typical questions we might be asked. Okay, let's start off. In the first one, we're going to have now this question to do. So we're asked to sketch each pair of curves on the same diagram showing the coordinates of any point of intersection with the coordinate axis. So we need to sketch each of these. So we've got 2 to the x and 5 to the x. So we need to show these now. We're going to have the exponential functions for both. 2 to the x isn't going to grow as fast as 5 to the x. They will, though, go through the same point. So what we'll have then, 2 to the x will look something like so. So that point is going to be 0, 1. We're going to come up here and we can label this up. Y is equal to 2 to the x. So if you wanted to pick some points, 0, 1, we'd have 1, 2, 2, 4, 3, 8, 4, 16. What we're now going to do is look at the next one, and that is going to be 5 to the x. So what we'll do will be below, just here, we'll come up, then we'll come through the same point, but this time we're going to now grow a lot quicker, and that will get a lot steeper, and we can see this point right here. So let's just have a look now to the left. So we know that this is going to be the point 0, 1 for both curves. This is the x-axis, this is the y-axis. Let's just take a point just here. Let's say x is equal to minus 1. So 2 to the minus 1 is going to be equal to 1/2. And then 5 to the minus 1 is going to be equal to 1/5. So we can see for these values right here that now y is equal to 5 to the x will be below 2 to the x. Of course, it will never be equal to 0, and the x-axis is still an asymptote, but we can simply show now 4. As this gets very big and very negative, we can see that it's going to be below. So that now is 5 to the x and 2 to the x. Let's do the next one. Y is equal to 3 to the x, and y is equal to 1/3 to the x. So let's go ahead and do that one. What we're going to have now is 3 to the x. 3 to the x is going to be now the exponential growth, so we'll come up here like so, and we'll come through the point 0, 1. We'll do something like that. So y is equal to 3 to the power of x, 0, 1, as we would expect. Again, we don't see the asymptote because it's the x-axis, but if we wanted to put it on just for that, I'm just looking ahead, this one right here, we're going to need to have some appreciation of it. So you might want to put it on anyway. So what we have is, if we have 1, we have 3, if we have 2, we have 9, if we have 3, we have 27, and that's going to grow. Let's now look at 1/3 to the x. So we could write this as y is equal to 3 to the minus 1 raised to the power of x, which would give us now 3 to the power of minus x, which is just a reflection now in the y-axis. So we would, and I'd actually write it because my curve sketching, especially on here, is never that accurate. So we could say y is equal to 1/3 to the power of x. So for example now, if we took at this point right here, let's take now x to be equal to minus 2. So let's just grab this point here. Let's take x to be equal to minus 2, and let's take x to be positive 2. So if we have now 1/3 to the power of minus 2, that is the same as saying 3 over 1 to the positive 2, which is going to give us 9. In the same way, we would have 9 just here. So we've got now minus 2, 9, and we've got now 2, 9. And that makes sense, as we're simply going to have now minus 2 minus minus 2 is going to give us 2. So that's what we have, and it gives us some kind of idea. In terms of showing where these graphs meet, for these ones right here, we're only going to have this one point of intersection, and that's going to be now at this point where x is equal to 0. Okay, let's do the next one. Y is equal to 4 to the x. So we have another exponential function. This one is going to grow quicker than 3 to the x, quicker than 2 to the x, but not as quickly as 5 to the x. So again, let's go ahead and draw that. We will have now the exponential function. It will look something like this, and it will get very big very quickly. So as x gets very large, this is going to get very large. Again, we're going to have 0, 1. That's the point that it's going to go through. Y is equal to 4 to the power of x. We have the x asymptote, now the x-axis as an asymptote. What I'm going to do now with the next one is just copy this, and I'm going to move it. If we consider now, all I'm doing with the next curve is translating it down by 1 unit. This is the f of x plus a. So this time I just move it down here, and we end up now with the point 0, 0. So if that had been plus 1, I would have moved it up. So this point now is going to be 0, 0. We need to show an asymptote on here, and that is going to be the line y is equal to minus 1, as we've dropped it down from the x-axis where y is equal to 0. So we have y is equal to minus 1. And this is a graph of y is equal to 4 to the x minus 1. It's simply now of the form f of x plus a. And in this particular case, we got 0, minus 1. Okay, so that's what we end up with, and that's what it looks like. Right, let's look at this last one. This last one is quite interesting. We know what 2 to the x looks like. We have now a transformation, and there are two different ways that you could look at this transformation. If we consider 2 to the x, 2 to the x is just a standard, straightforward exponential curve passing through 0, 1. What I'm going to do is just drag this downwards a little, and then we'll just move this down. Let's go and move that like so, and that will go just there. So again, that point is going to be 0, 1. There are two different ways I could look at this. This now is of the form the f of x plus a. So we're looking now at a horizontal translation, and in this particular case, we would move this 3 units to the left. So this is our original, 0, 1. Y is equal to 2 to the power of x. And again, this is going to grow. It's going to get very big very quickly. X-axis and then y-axis. Okay, let's consider rewriting this though. So let's think about now when x is going to be equal to 0. Now, if x is equal to 0, we've got 2 to the power of 3, and that is going to give me this point just here. And that point is going to give me 0, 8. So what we end up with now is a horizontal translation of the 3 units. You could also look at this, and I'll just go ahead and sketch this. So what we're going to have is something that looks like that. Let's go up, and we'll have something, give or take, like so. It will obviously be a bit neater than that. Another way to look at this now is y is equal to 2 to the power of 3 multiplied by 2 to the power of x. So we can look at this as a multiplier of 8. So that's roughly what they're going to look like. So as we can see, we can apply these transformations that we've already met in the past. Okay, let's move on and look at another question. A curve has the equation y is equal to 2 plus a to the x, where a is a constant and a is greater than 1. In part A, we're asked to sketch the curve showing the coordinates of any point of intersection with the coordinate axis and the equation of any asymptotes. So let's just focus on y is equal to a to the x. What I'm going to do now is just go ahead and sketch that. So what we'll have then is the following. If we have y is equal to a to the x, we know that this is going to model growth. So we'll start like so, and we'll come up. We'll come through the y-axis at the point 0, 1, and that will get very big very quickly. So at the moment we've got 0, 1. What we have here, and I'll just rewrite it, y is equal to a to the x plus 2. This is of the form f of x plus a. And all we'll do is lift this up by 2 units. So we'll have now an alteration in the asymptote. So what I'm going to do is just pick it up, and I'll just move it out of the way. Let's just put it there. And what we've got now is the following. We're going to have the asymptote just here, and that will be the line y is equal to 2. So we can write now y is equal to 2. If we consider that this point was 0, 1, we've now moved it up by 2 units, so it's 0, 3. And we can label this up, y is equal to a to the x plus 2, or 2 plus a to the x. It says, given also that the curve passes through the point 3, 29, find the value of a. So let's just go ahead and sub these in. So 29 will be equal to 2, and then we're going to have plus now a to the power of 3. So at this stage we subtract 2 from both sides, so 27 is equal to a cubed. Taking now the cube root to both sides, we can see that a is equal to 3. So what we have here is the graph of y is equal to 2 plus 3 to the power of x. So nice and straightforward. We're just considering now this transformation. And it's a straightforward transformation, but we do need to show the asymptote. Okay, let's look at another one. Which way we go? We need to go back the other way. So let's find another question. Right, let's go this way. So this one, it says the diagram shows the curve with equation y is equal to 2 to the x minus 5, which intersects the coordinate axis at the points A and B. We're asked to find the length AB correct to 3 significant figures. So what we have is an exponential curve. We've got y is equal to 2 to the x, and now all we've done is translated this down by 5 units. So let's consider now A. What we've got then is A, and with A we can say that x will be equal to 0. So at A we've got x is equal to 0. So y will be equal to 2 to the power of 0 minus 5. So we can have y will be equal to 1 minus 5, and we can say that A will have the coordinates 0, minus 4. So that's the point just here. So all we're going to do is go ahead and write that on. So what we have then is 0, minus 4. If we now consider this point right here, and that's B. B we can write now, for B, we've got y equal to 0. So subbing that in, we're going to have 0 is equal to 2 to the x minus 5. So we can say that 2 to the power of x is equal to 5. We now need to solve for x, and we've seen this in previous videos. So we can take logs of both sides. So we can say log 2 to the power of x will be equal now to log 5. I'm just using base 10. So bringing the power down, x log 2 is equal to log 5, and then we can say now that x will be equal to log 5 divided by log 2. So that now gives us the coordinate. And again, we could write that correct to however many significant figures. That now is the exact value. And if I put that on just here, what we'll have now is the following. Log 5 over log 2, 0. So what we have is log 5. Remember, these are just numbers over log 2, 0. So what we have here is just a basic right angle triangle. So all I'm going to do is use Pythagoras. So if we look at this right here, what I've got now is 4. I've got a length of 4. So let's go ahead and write 4. And then I have this value, which I'm going to put as an exact value in the calculator. So we've got log 2. So this length right here will be the square root of this quantity squared plus this quantity, as that's just like a little right angle triangle. So that's AB. So let's go ahead and put this through a calculator to get some idea of the magnitude. So in the calculator we have now, and we can use any base, I've just used base 10, we've got log 5 over log 2, and that gives us now 2.32. So we can say that that's approximately equal to 2.32. We can say that AB will be equal to the square root now of 4 squared plus now 2.32 ... squared. And that's all we're going to do in the calculator. So let's go ahead and do that. So I'm going to square this quantity. I'm going to add it now to 16, and then I'll square root the answer. So we're going to have this now. That's going to give me 4.625. They want the answer now to 3 significant figures. So we can say 4.63, and that's units. So that now gives us AB, the length. So all we've done is gone ahead and solved the equation and plugged the values in. So there's some basic work now looking at exponential graphs of the form y is equal to a to the x, where a is a positive constant.